Thank you for the presentation and good afternoon, everyone. The work that I'm going to present is about the failure analysis of nano-filled ultra-high performance concrete structure. This work is co-authored with Professor Lonetti, Greco and Penna and Drs. Leonetti and Pascuzzo. In recent years, the main limitation of ordinary concrete have been overcome by using a ultra-high performance fiber reinforced concrete, abbreviated as UHPFRC, due to very high compressive intensity strength, ductility, and durability. A recent study has showed that incorporating nanofillers in UHPFC structure lead to improved performance in terms of strength and fracture toughness property. Several nanofillers are used as a reinforcement, for example, carbon fibers, graphite nanoplates, carbon nanotubes. So, despite the high number of the experimental investigation, a few numerical models exist in the current literature that analyze the effect of nanomaterials in UHPFC structure. So, for this reason, for reproducing graph propagation of phenomena, we develop an efficient finite element modeling that combine the moving mesh technique for reproducing the geometry evolution caused by the crack advance, the international integral method to extract fracture variables at the crack front, and R curve concept to capture the ductile behavior of this structure. So, besides the spatial and material system, the moving mesh introduces a new mesh coordinate system in accord to which mesh nodes can move independently from material nodes. So the various frames are linked by proper mapping function, which are needed to express all governing equation with respect to the mesh configuration. Moving mesh adopts the Laplace regularization approach for reducing mesh element distortion. The M integral expression, starting from the J integral applied to superimposed state, formed by two admissible files, the actual one, for which stress intensity factor would evaluate, and the auxiliary one whose solution is enough. Finally, in the recurve model, the fracture resistance, expressed in terms of fracture toughness or energy, is a function of the equivalent crack extension only. Now, in this slide, show the procedure for evaluating hair curve, starting from an available experimental Lloyd curve. It consists in three different steps. Step one, performs finite element analysis for calculate load mid total deflection and stress intensity factor as a function of the relative crack depth by varying the latter in a discrete manner after assuming a constant depth increment. For each crack depth, the value of the related shape function V and K are found. The second step performs a curve fitting analysis to obtain an analytical surrogate analytical model in terms of closed form expression of V and K. The third step performs three further sub-steps using the obtain analytical expression. So at the beginning, the initial value of the shape function V and the effective elastic modulus are evaluated. After that, the relative crack depth for all points of the measured load displacement curve are evaluated. After finally, the critical stress intensity factor for all relative crack depth value are evaluated and used to derive R curve. The crack propagation mechanism is managed by an automatic algorithm. The analysis starts by defining geometry, mechanical property, boundary condition, and initial mesh configuration. During the simulation, the loads are slowly increased. For each increment, the stress intensity factor at crack front are extracted and used to evaluate crack onset condition and direction of propagation. When this condition is fulfilled, the propagation occurs. So the moving mesh advance the crack tip to simulate the propagation. During the propagation, the elements around the crack tip are distorted because of the mesh motion, and remeshing events occur exclusively when the quality of the mesh is compromised. Now, to verify the reliability of the present method, we consider two crack problems. The first is a 4-point bending test under poor mode 1 fracture condition. We consider 4 different mixtures of UHPFRC. One without non-enhancement, and the other contains 0.1, 0.2, and 0.3% graphite nanoplates. So this graph shows the error curve obtained by using a numerical procedure explained previously in terms of critical stress intensity factor as a function of the crack extension. Instead, this graph compares curve load versus deflection of midpoint of the beam predicted by the proposed method with the experimental prediction. So the results are in excellent agreement with them. In addition, this graph shows the great influence of the amount of GNP reinforcement on the overall peak load and post-peak behavior. The second example involves an asymmetric 4-point bending test under mixed mode fracture condition. We analyzed 4 different geometric configurations. This case differs according to the distance C and C1 of the load point and the pre-crack location, both measured from the midpoint. In particular, case 1 involves fracture under poor mode 2, and the other case involve mixed mode crack propagation. The results in terms of load versus crack mounts like displacement show how the peak load increase at increasing value of mode 2 component over mode 1 component. And this can explained by increasing the crack path tortuosity, as we can see from the finally crack trajectory. Finally, here we can see the crack evolution for case 1 and case 3. So, in conclusion, a novel finite element modeling approach for the numerical simulation of crack propagation phenomena in nano-filled UHPFRC structure is proposed, which combines the moving mesh technique, the interactional integral method, and the recurve concept. The proposed strategy has been validated through comparison with experimental data, and thus denoting that if the error curve is accurately calibrated, this strategy ensures accurate prediction. So despite extensive formulation, the moving mesh technique reduced considerably the recourse to remeshing events. And finally, the proposed procedure can be effectively employed for simulating crack propagation phenomena under poor mode 1 and mixed mode condition in nano-filled UHPFRC structure. Thank you for your attention.